to make this problem, it was shortly after I had made a trip to Charlotte and had to drive back from Charlotte. And as you're driving back from Charlotte, especially if it's like 4 or 5 o'clock, you basically sit there for the first you just sit there until you get to Lake Norman. And then once you get to Lake Norman, you can run, 75 the rest of the way. So, no more than that. Well, actually, Statesville's not 70 miles an hour speed limit, is it? Statesville goes back down. Especially with and right now there's the construction, so. Yeah, it's low through Statesville. You gotta slow down through Statesville, but. Yeah, you do not try to be anywhere between mile marker 0 and 36. Anytime between like 4 o'clock and 6 o'clock in the afternoon or in the morning. Well, if you're coming back this way, it's 4 o'clock and 6 o'clock. If you're going in, it's the mornings when it's so bad. I was going so fast. It was an early flight. Yeah. On the way back. Yeah. Stopping every time. Yeah.
Except for me. That's right. I mean, just normal stuff, I guess. The only mistake that I made is I forgot to put my hands on the wheel phone and just kind of like, so, and I actually forgot I had a Mac in my car, so I'm glad I didn't try to search it. Because I really forgot about it. No. She freaking made fun of me. My new favorite thing is when Miss Wallace is saying something to her, I just say right.
Alfredo. Good. I thought he was a nice kid. All right. Alfredo is a bully. I'm going to tell him. Bully has been the word of the week at daycare.
Margaret gave in the peer pressure.
Alfredo, you need to be nicer. All right. So let's look at the next one. So that is our average speed. It is not the speed at a certain point because probably you were sitting still whenever you were at mile marker 15, but you were going 70 miles an hour whenever you were at mile marker, 63 or something.
Fair to say that we don't have enough information to determine that.
No, we can figure this one out. So,
would there be multiple points that could change at any given moment?
Yes. Yeah, but since it only asks us for average, we can figure it out. If it asks us at a certain point, we can know.
Point, there could be multiple answers, right?
Yes. Well, given the information we know, we wouldn't have enough to give an exact answer, but there would only in reality be one, but we wouldn't be able to figure it out from this information. So, in this particular case, these notes usually come right around homecoming time, so this is appropriate. In fact, you got to vote today, right?
Yeah.
So, vote if you haven't voted. Some beautiful young lady's future depends on it. Their life will be different.
There should be a homecoming club for just guys.
All right, so a function gives the number of students who have voted for homecoming queen as a function of time. Time is measured in hours since 8 a.m. on the day of voting. What is the average rate of change of f of t on the interval from 0 to 4? Explain this rate of change in context of the situation. So, In context of the situation means you got to tell me what this means for votes and hours, right?
What's
So-
the interval part mean?
In context. This just means 0 to 4. What does our T stand for? Time, and it's measured in hours. So in this case, 0 to 4 would be your first 4 hours of voting. Or you could say in this case, 8 a.m. is when it begins, so you could say 8 a.m. to noon is when you're dealing with it here. But just first 4 hours of voting is fine. And then F of T is number of votes. So number of people who have voted. And so if I want to know from 0 to 4 what the rate of change is for that, rate of change just means slope. So I'm using 0.35 and 4.256. Be careful and don't use the last one because it only asks us from 0 to 4. So you're going to do slope. So 256 minus 35 over 4 minus 0. So 256 minus 35 is going to give us 221. And 4 minus 0 is 4. And 221 divided by 4, 55.25. And we have to explain this within context of the situation. So this is my change in, well, it's actually change in F of T, but change in Y over change in X. Or we can think of it as change in F over change in T. So what did that numerator stand for?
The numerator stands for the time.
It is votes. Because when we do slope, the Y is on top. And then this is hours. So this is votes per hour.
Like, is that what it's looking for?
No, you got to explain it in words. So, but getting the correct units really gets you in the right direction here. So, what time interval are we talking about here? 8 to 12. So we can say from 8 a.m. to 12 p.m. Or if you just said for the first 4 hours of voting, or if you said from T equals 0 to T equals 4 hours, any of that's fine. This is most specific because it's given the actual times. But from this time to this time,
Votes were cast at a rate of 55.
exactly. So votes were cast at a rate of 55.25 votes per hour. Yes. Yes. Thomas is perfectly okay with it. Daniel is protesting.
If my answer is wrong, but the explanation justifies it, do I get a point?
It depends on how the points are set up for the question, but if the usually the rubric, if it's a 2-point question, the rubric would have a point for the correct answer and a point for the explanation. So yes, you could get a point for the explanation if it was a 2-point question.
No matter what, I should get one.
Yeah. Now, sometimes these are just 1-point questions where you got to have all of it. So if you only had the answer or you only had the explanation, you wouldn't get it. So it just depends on what the rubric is set up for, like on those problems. Okay, but this is the average rate of change. This is not calculus. This is slope. This is math 1, right? Really, honestly, we could probably figure it out even if we didn't know how to do slope because we could know it would be votes per hour. We'd probably have a hard time. My math 1 kids couldn't do this if I gave it to them worded like this. But they eventually don't have the math that they could do it, right?
I can do it.
Okay, so
You sure?
here is what I sometimes just call a naked problem, right? Yeah. The naked problems have no context whatsoever, right? But it asks us for the average rate of change of f of x on the interval from -1 to 3. So if we just get like a quick thought of what this graph looks like, it's a quadratic. What has happened to it with this -2? Right 2 and up 1. So right 2, up 1, that vertex of that parabola is going to be right here. It's going to look something like this. So at, I need to really, at -1, really draw that on out. -1 is going to be somewhere like way up here, right, on that graph. And then 3, it's going to be like maybe about right here. And so we're looking at the rate of change, which is the slope between those 2 points. But we don't want to have to like graph this perfectly to figure that out. So we just really need the coordinates of those 2 points. How do I find the coordinate that goes with -1? Plug it in. So I'm going to do f of -1, which is going to be -1 minus 2 squared plus 1, which is going to give me -3 squared plus 1, 9 plus 1, so I get 10. So that tells me I'm dealing with the point -1, 10 here. And then if I want to find the other point for the other end of this interval, I just have to do f of 3. So I would have 3 minus 2 squared plus 1, which is 1 squared plus 1, which is just going to give me 2. So I got the point 3, 2. Yes. So if I want to find the rate of change here, it's average rate of change. I'm just finding the slope between those endpoints. So I would do 10 minus 2 over -1 minus 3. So 8 over -4, which is -2.
Why is 10 and 1 divided?
You could do it the other way. You could do it 2 minus 10 over 3 minus -1. That
doesn't really matter as long as you have the x y.
Right. It doesn't matter. It just, all that matters is like this 10 and -1. If the 10 comes first, the -1 has to come first in the bottom. Yeah. You just have to be consistent with which one you're letting the x1 and y1 be. So the rate of change for this one is -2. And let's look at this graph I have here. So right here was my point at -1, 1. Right here was my point at 3, 0. Right here is the line that goes between that. And so we can find this, we just found the slope of that line, which you can see from the graph is -2.
I like the graphs. You can see them.
Yeah. Now, where we're going from here. This is my average rate of change. But let's say what I really care about is my rate of change at a specific point. So like, I'm going to put this point here. That's not showing up. That's because it's too big. Let me put a point here. So I've got this point right here. Let me label that. Let's call it A so you can see it. So I've got this point right here. So if I want to know the rate of change at that specific point, it's not going to be equal to -2. It looks like it's maybe slightly steeper right here than it is over here at -2, so it might be -3 or -4 or something like that. But what I want to do is I want to find the slope at a certain point, and that is going to take calculus. Average rate of change does not take calculus. So let's look at how to do this. So here I have another Desmos graph that we're going to look at. All right, so, oh wait, I closed the wrong one. Okay, here we are. So I have a function. The particular function I have chosen is f of x equals square root of x plus 7 over x minus 3. And don't worry about how complicated all this stuff is, although I felt pretty proud of myself for coming up with this so that it all worked. But let's say that we have a point x f of x, and we are wanting to know the slope of the tangent line at this blue point that I'm pointing to right here. Okay, and let me see what it shows up here. All right, so this blue point right here, I want to know the slope of the tangent line. So it really, like, you can picture what it should be like. It should just touch it at one point right here. So what I have done is I have made another point on the graph somewhere that I am calling a f of a. And so a f of a is somewhere over here. So if I want to know the slope of the tangent line, then what I need to do is I need to take a and I need to drag it over here closer and closer and closer and closer and closer to x. Right? If I can get it right on top of x, then I have a picture that is just my tangent line. I could also do that over from this side. So if I have this point A, if it gets closer and closer and closer to x, you can see that line gets closer and closer to looking like it just touches at one point. This is going to be the case no matter what your function is. So like I could change this to a completely different function. I could make it x. Oh, let's see. I think I've got it set up where it's going to work okay. X minus 3 to the second minus 4. Okay? So I got a quadratic. Where'd my A go? Let's move it back up. Oh, it's moving fast. All right, so here's my... Uh-oh. There we go. Okay, so if I want to know the tangent line at this point, I move my A closer and closer and closer to x, and eventually it will end up right there where the tangent line is, right? So, so that's the idea that we're dealing with no matter what type of function. And it doesn't matter where x is. I could move x down here. Well, now as I move A closer and closer, that's pretty close right there to being a tangent line, right? So that's the idea that we're working with here. So here is what we're dealing with. I had 2 points. They were x, f of x, and a, f of a. One of the reasons that I used that annoying notation on the Desmos activity you were doing earlier, where I did 0 f of 0 and 0 f of 1, or 1 f of 1 and all of that, is because I need you to kind of understand what I was talking about when I did x f of x, right? So, so if I want to find the slope of this line, right, then I would do f of x minus f of a over x minus a. Or if I wanted to, I could put the a's first, but generally when we do limit definition of a derivative at a point, we use the x's first. So I'm just going to do it that way. So that's just slope formula. Subtract your y's on top, subtract your x's on bottom. So this would give you the slope of, if we're still thinking about that graph, that would give you the slope of the line that passes through x and x f of x and a f of a, these 2 points right here. Well, if we want this to be a tangent line, we want, actually it was probably going the wrong way. We want these points to get closer and closer and closer together, right? We want these points to reach each other. So what we want is we want to do the limit as x approaches a. actually was moved. I moved the A on most of mine. I guess I should have moved my X because your X is getting closer to A. This is what we call a derivative. And derivatives are basically the whole, there are three major parts of calculus. Limits are needed to create derivatives because it's the basis of this. Then the next part, which is what we're starting into now, is derivatives, which is a huge section of calculus. And then later we'll get to integrals, but that's much later, so we're not worried about those right now. So this is how we find the limit definition of a derivative at a point. So let's look what so this right here you need to know and have memorized. So you might want to put some stars around it, a box there. You need to know that and have it memorized. It's basically just slope formula with the limit as x approaches a. Okay? So here's what a question is going to look like. It's going to say, find the instantaneous rate of change. This is one way it could be asked. Instantaneous rate of change of f of x equals square root of x plus 1. So instantaneous rate of change is the slope of your tangent line. Okay, because it is that speed at that point. It is not how fast you go on average. It is like if the police car is sitting there with the radar gun and shoots your car as it's going down the road and it says you're going 85 miles an hour, it's your speed at that point, right? So it is the slope of the tangent line. So if you see instantaneous rate of change, that is slope of the tangent line which can also be called the derivative at that particular point. A little notation that I want to use here is I'm going to write this as f prime of 3. So when I said prime, I would just put like a little tick mark right behind my f. I'm going to write this out just so you know the notation. So this is read as f prime of 3, and it means the derivative of f when x equals 3. So this is just some notation that you might run into sometimes, because there's a lot of different ways that this could be presented, but this is one of them. So the derivative is the slope of the tangent line. So anytime I say derivative, I'm meaning the slope of that tangent line. So if I want to find the instantaneous rate of change, that's the slope of the tangent line or the derivative at 3. So I would use that formula. So the derivative is always the limit as x approaches a of f of x minus f of a all over x minus a. I'm just writing the formula down that we had before, so we're looking at it right here. Now, in this particular case, our a is going to be 3 because that's the point that we're looking at. Actually, I should, instead of saying f prime of x right there, let's change that. That should be f prime of a, because that's the point we're plugging in. So our a is 3. So f prime of 3 is going to be the limit as x approaches 3 Now, here we have to put f of x. F of x is the formula that they gave us right here. So we're just plugging that in right here, which will look like this, square root of x plus 1. Now, f of a, in this particular case, our a is 3, so we're finding f of 3. That just means plug 3 into f, right? That's what we were doing whenever we were doing this formula. If we needed to know f of 3, we just plugged 3 into that equation that we kept using, and that gave us our y-coordinate, right? So f of 3 is going to be, in this case, 3 square root of 3 plus 1, which is the square root of 4, which is 2. So we got minus 2 out here. And in the bottom, we've got x minus a, and that a was a 3. It is discontinuous at 3. But if I plug in 3 right now, and this is something we need to do because some of you guys are messing this up on test stuff. If we plug in 3 right now, I would get square root of 3 plus 1 minus 2 over 3 minus 3, which would give me 2 minus 2 over 0, which is 0 over 0. What does that tell me when I get 0 over 0? We've got to keep going. It's indeterminate. It is not the answer. It does not mean does not exist. So we have to keep going. So how could I solve this limit? Multiply by the conjugate. Yeah. So we got to multiply the top by square root of x plus 1 plus 2. And the bottom by the square root of x plus 1 plus 2. And there's one of you on the quiz that you just about had it right, but you forgot to multiply the bottom. That's somehow a very common error. Okay, so once you multiply by the conjugate, in the numerator, you're distributing. Square root of x plus 1 times square root of x plus 1 is x plus 1. Whenever you multiply square root by itself, it just cancels out the square root. Then you would have square root of x plus 1 times 2. So we would just have to write that 2 times the square root of x plus 1. Or don't write it out. Let's get this. And then the middle part right here, you get minus 2 square root of x plus 1. So what happens with those two right there? They cancel. So if you don't want to write them at all, that's fine, as long as you understand why you don't have to do that. And then negative 2 times 2 is negative 4. And then in the bottom, don't multiply those together because we want something to cancel anyway. So we don't really want that to happen. So if we keep going, we're going to have x minus 3 over x minus 3 square root of x plus 1 plus 2. And what can happen with my x plus 3's? They can cancel. And so at this point, I do still have a 1 in the numerator because you got to keep that 1 in the numerator. At this point, you can plug your number in. One thing that it was really, some of you were messing this up in one direction, some of you were messing it up in the other direction. Whenever it comes to limit notation, there were a few of you, particularly one of you in the back row back there, that barely used limit notation at all. Like, maybe wrote it on the first step and then abandoned it completely. So you can't do that. You got to keep limit notation the whole way. If you want to write it after you actually do the problem, that's okay. I get it. Like if I'm working something out quickly, I skip it too. I understand it's there, but you got to keep it the whole way. But once you plug in the number, you do not use limit notation anymore. So far we haven't plugged in a number. We've just been factoring, canceling, multiplying by conjugate stuff. So at this point, I'm ready to take 3 and plug it in. So I do not use limit notation anymore. I would just have 1 over the square root of 3 plus 1 plus 2. On the other hand, those of you who are the complete and total opposite of Daniel, some of you kept the limit notation way too long. Like you still kept limit notation here and in the next step until the very end. So some of you were like so scared of not having it correct that you kept it too long. Once you plug the number in, you do not need limit notation anymore. So this is 1 over. I don't think I counted it wrong if you kept it too long at this point. Now, there might be a point towards, later on where I might would be a little pickier on that. But if you dropped it too early, I was more likely to count off for it. So we got 1/4. And that means that is our slope when x equals 3.
So it's 1/4. So 1/4 is the instantaneous rate of change.
Yes, instantaneous rate of change.
X equals 3.
Yeah, and so let's look.
That's the derivative of that function at x.
Yes, yes. And so we could, sometimes we'll see it written like this. Yeah, so sometimes we'll have an f prime of 3. The derivative of the function at 3 is 1/4. Lots of different ways to say it. Here's what it looks like. Let's change this to square root of x. Was it plus 3? There's the function. Plus 1. Okay, and then my a was at 3, so I'm going to move that over here to 3. And so here's what we were doing there. As x approaches a, you can see we get close to, it disappears if I go exactly there, close to this line, and it has a slope of up 1 over 4. So graphically, that's what we were doing. All right, let's try another one. All right, so the position of a particle moving along the x-axis is given by the equation. What is the velocity of the particle at t equals 1? Okay, we're doing pretty much the same thing here because position is like our distance traveled, right? And velocity is our change in distance over our change in time, right? So that is the slope, because whenever you graph this, this would be our position, which is our distance, and this time. So if we did the slope, it would be change in distance over change in time, which is our velocity. So we're looking at t equals 1. So what we'll be doing here, we got to use that formula, limit as x approaches a, but in this case, instead of putting a, I'm going to put a 1, of f of x minus f of a, but my a is 1, so I'm going to put a 1 right there, over x minus 1. And so f of x is just our formula for f of x. F of 1, I need to figure out what that is. F of 1 is 1 plus 1 squared. So 2 squared, which is 4. So that will go right here. And then I can plug all of that stuff in. So limit as x approaches 1 of x plus 1 squared minus 4 all over x minus 1. Okay. If I plug in 1, what do I get? 0 over 0. Which is indeterminate, which does not tell me that it doesn't exist or that it equals 0. It just tells me, I don't know yet. I got to keep doing something else. So what should we do for this one to figure out this limit?
Do you need to expand?
Yes, we will expand. So you'll get x squared plus 2x plus 1 minus 4 over x minus 1, which I can combine my like terms, so x squared plus 2x minus 3 over x minus 1. Alright, what else should I do?
Could you, the one, could you, I don't know, like, combine it again?
Say that again.
Could you do, factor it again?
Mm-hmm.
And then that would cancel out.
Good. So if we factor, I've got x plus 3, x minus 1, if I factor that numerator. And then I've got an x minus 1 in the denominator. So those two will cancel. And once they cancel, now I can just plug in my number. Once I'm plugging in my number, I drop my limit notation. So it's just going to be 1 plus 3, which is 4. Okay, questions? Yep, just 4.
I can do this.
Good.
So our answer would just be 4. There is, f prime.
Yeah, and so you could say f prime of 1 equals 4 is one way you could write it. For this particular question, it's asking for the velocity, so you could just say it's 4. You know. All right. So, 6, which is our last one, right? Okay. All right. So, I've got 1 over x.
Negative 1 is for that job.
So, it asks me for f prime of negative 1, which does not mean f of negative 1. It means the derivative of f at negative 1. So, when I got this little tick mark right here behind my f, that's f prime of 1, which shows me I'm looking for the derivative. So, if I'm looking for the derivative, I got to use that limit as x approaches, in this case it's negative 1, of f of x minus f of negative 1 over x minus negative 1. And so f of x, that's just the formula. We just put it right here. We have 1 over x. F of negative 1, I need to figure out what that is. That's 1 divided by negative 1, which is negative 1. So minus negative 1 all over x plus 1 here, because that double negative will be plus. I also could do that same thing with that double negative there. Let's do that. Limit as x approaches negative 1 over x plus 1 over x plus 1. Now, there's a couple ways that you can simplify this. You could do common denominators and flip and multiply. My favorite way to fix this problem here is to multiply the top and the bottom by x. Okay, it's okay to multiply top and bottom by x, because if you do that, it's still equivalent. So I could distribute my x in the numerator, and x times 1 over x is just 1, because the x's will cancel. Okay, so whenever you do x times 1 over x, this is like x over 1, right? And so when you have an x in the top and the bottom, they cancel, so that's just 1. And then x times 1 is going to give me x. Don't distribute the denominator, because you want things to cancel, so it's better if they are factored. And so I've got 1 plus x and x plus 1. Can those cancel? They can. Because the order doesn't matter there. Now, if it was 1 minus x and x minus 1, we could not cancel those. But I can cancel these. So I'm just doing 1 over, and I'm going to plug in my negative 1 right there. So I get negative 1 for my answer.
So literally, if we just plugged in -1, we got the same answer.
You would have gotten the same answer here.
It doesn't work all the time.
It does not work all the time.
How did you get the denominator after you, when you're distributing the x? Okay.
So up here, I just distributed my x to get this 1 plus x. Down in the bottom, I did not distribute.
Oh.
And the reason I did not distribute is because I wanted to cancel something with something in the numerator. So it's going to just be more likely to cancel if I don't distribute there. Yeah. And so if you distribute, you'd have x squared plus x, but then you just have to factor it back out to cancel. I think it's likely this is going to equal 1, but let's work through it to see. So this is going to be the limit as x approaches 1 of f of x, which is 1 over x, minus f of 1. What is f of 1? It's just going to be 1, because if we plug in 1, that's just 1 over 1, which is 1, right? Over x minus 1. So we're going to have to do the same thing here. Multiply the top by x. Multiply that bottom by x. So this will be the limit as x approaches 1 of, when we distribute, x times 1 over x is just 1. X times -1 is negative x over x times x minus 1. Can x minus 1 and 1 minus x cancel? No. They can't factor the way they are. So we want to do what Addison said, and we want to factor out a negative out of that numerator, which is going to make it negative x minus 1 over x minus 1. So whenever you're doing that, what I did there is like if I've got 1 minus x, if I factor out a -1, that would make this negative x plus, or -1 plus x, which would be, if I rewrote it, x minus 1. So this top part right here is really close to being able to cancel with the bottom. They're just backwards, which matters. Up here it didn't matter because it was addition, right? So addition we can just switch the order, doesn't matter. But with subtraction we can't do that. So we're just factoring out that negative. So anytime you see that happening, if you factor out a negative, it's going to switch that order, and then these two can cancel. And so when we do this, we're going to plug in 1. We got that negative on top. It's got a 1 with it, even though it's not written there. So -1 over 1. We also get -1 for this one. Yeah, so both of those are -1.
So anytime we ever see, no, never mind, because it changes with the function.
Yeah, it changes with the function. So this would only apply for 1 over x here. So if I need to find f prime of -2, limit as x approaches -2 of very good. So we're going to have the limit as x approaches -2 of f of x is just 1 over x. F of -2 is going to be -1/2 for this. So it's going to be plus 1/2. And we just get that by going up here to the original equation and plugging in a -2. And so that's over x plus 2. Now, at this point, some of you may prefer getting common denominators here because it's not quite as straightforward, but it's still not bad. I still like to do this if I multiply by both denominators, if I multiply by 2x on top and bottom, look at what will happen when I distribute. If I do 2x times 1 over x, then the x's would cancel, and I just get 2. So I got 2. And then here, I've got to do 2x times 1 over 2. 2x times 1 over 2. 2's cancel this time, and I just get x. So I got 2 plus x over 2x times x plus 2. And so this 2 plus x can cancel with this x plus 2. At this point, we got a 1 left in the top, so we got 1 over 2 times negative 2, which is negative 1/4. Now, while looking at this problem, you might be saying to yourself, we were kind of doing the same thing each time there, right? And you might be thinking to yourself, there's got to be a better way if we're finding the derivative at all these points. There is, and I will show that to you tomorrow. But for right now, we're going to do this. So your homework is going to be from page 131. It is 1 through 10. And let me tell you about it real quick.
They just all like exactly.
All right, so
You get one to that last
1 through 4 deal with graphs and ask you to estimate the slopes, and give certain things. 5 through 10 are going to ask you to find the slope of the tangent line at the given point. They give you, whenever they give you the point for this, I was just giving you like x equals negative 1. They give you negative 1/8. So that's where x equals negative 1. Okay.
So we don't do, so can we even use the number 8?
Well, you can, because whenever you do, like for example, like that one, this is number 5. F of x equals 3 minus 5x. Well, if I do, I'm going to do the limit as x approaches negative 1 of f of x minus f of negative 1 all over x minus negative 1. Right? It's a negative 1 right there. So it's going to be the limit as x approaches negative 1 of 3 minus 5x. So f of negative 1 is what I'm going to get if I plug in
So it should be 8.
right here, which is going to be 3 plus 5, which is going to be 8. So it's going to be that y coordinate right there. So you could skip ahead and just use that y coordinate
we don't
instead
have
of
to
showing the
show-
work.
We can just.
Yeah.
Are we going to use this for homework?
So like this right here is your f of negative 1. So you don't necessarily have to show work. You can just plug it in.
It almost makes sense, but is there
So close yet so far away.
that one step of like figuring out how to simplify it that my math creativity doesn't kick in?
Yeah.
We got a whole other semester this year.
No, I like this.
This makes sense. I got this.
I love long, drawn-out, difficult problems. This one's not too long drawn out.
I just don't like when you mess up the second step.
It is frustrating if you like miss a negative on the second step.